We're very pleased and honored to have Professor Shuhong Gao, who's one of the top experts in the world on computer algebra. He's going to speak on recent progress in computing Grobner bases.
Okay, thank you, David. It's my honor to speak here. Everyone, I would like to talk about some recent work about computing Grobner bases, especially our work, joint work with my co-author Frank Volny. He was my former PhD student. After finished PhD, then he went to NSA. And my other colleague is Mingsheng Wang. He's a professor in Chinese Academy of Sciences in Beijing. So while he was visiting me in Clemson, we kind of had this ideal and tried to work it out. So I also visited China quite a few times. Okay, so I'd like to talk a little bit about the background about the problem, about complexity of solving polynomial system. Just two examples. Okay, so in general, then I try to talk about the Buchberger's algorithm and the issue with it, and then mention some recent algorithm, but not at the detail. Just mention a few names of people. Then I just focus on the work of the algorithm we developed. So try to convey some ideal, just theoretical ideal. Okay, so that makes some comparisons. Okay, so you have a question, just stop me. Okay, so I try to this talk. Better if you had more example, but somehow I didn't put an example in there. So it's kind of both kind of theoretical in there. First, there are many problems in algebraic geometry. So, actually in mathematics in general, that involve polynomial systems. So there are basic questions. So like a formula. So if you are giving a system of polynomials like G1, Gm with n variable, the f could be depend on what you work with, rational numbers, real number, constant numbers, or in application like coding cryptography. Most of the work is finite field FQ or even F2. Okay, so given a system polynomial, the fundamental question is deciding if there is a solution, okay, in a recursion. So how do you know if there is a solution? Now, sometimes when you express geometry, actually you want to study more about structure, like if there are implemented solutions, you want to, give it any system polynomial, you want to know how many components, how to find components. So like those questions, okay, so those are kind of fundamental complication in algebraic geometry. And another problem in computer algebra is the point is called Selfie, complete free resolution. So you give a system polynomial, try to find all the relationship. That's called Selfie. I want to talk about that later on. How does it relate to Grobner basis? Okay, ideal Grobner basis there. Now also another problem is to compute the primary decomposition of ideals. Those tell you the irreducible components. At the same time, also tell you multiplicities in there. So I won't talk anything like that. But to do those things, the first thing you have to do is that you have to compute the Grobner basis to be able to compute the primary decomposition or if any irreducible components. So I won't talk about any of those. I just concentrate on Grobner basis. Now first, of course, we remember from high school, I give just one polynomial, right, with degree 2. So we know this quadratic formula, so we can solve this polynomial. We'll actually have a formula to say, you give me coefficient ABC, I can find the roots just by computing two roots, right? So that's the formula. And for critical polynomial, after that one, so people try to find formula for that one. So after this, because this effort, Gao developed this book series, and then later on number series, etc. So it all comes like that. And actually he proved that there's no formula for that using radicals. So that's one of the most important theorems if we teach abstract algebra. Okay. So, but we're not just interested in formula to find the roots. Okay, so because formula kind of give you a special, just particular algorithm for computing roots, right? But algorithm in general, I say this step, that step, do this, do that. There's much more general. Okay, so we were interested in algorithms to decide the root or to find the roots. Decide if the solution not just the one variable, but could be, so as I mentioned, could be any number of variable, any number of equations. Try to decide if there are solutions. Okay. So let me give you some more example. Like in this case, there's two extremes. Okay, to give a polynomial system. One extreme is that okay, I give you one polynomial, but the degree could be high. Okay, in this case, we call sparse polynomial. So the degree, like you write down the exponent, right, on the degree, like 2 to the 6 to the 2,000 something, and put these numbers. So if you expand out the number on the exponent, the degree is, well, you see, I measure by how many bits, okay? The length of the number, okay? The degree can be extremely high. So I only record the non-zero terms, okay? There are lots of zero coefficients. I don't write them down, okay? I don't represent them. So this is called sparse representation of polynomial. So, and also the field, you work with the coefficient field, the 2 to the something, that's very big. That can be any size. Okay. So now I give you a polynomial like this. I give you a polynomial of certain degree, write down in binary form, and how many terms, give down the term, the degree, right? Give coefficient, the big field I gave you. Now say, can you tell me if there is a solution in that field? Okay, just one variable. Okay. So this is called the sparse polynomial totality of deciding the solution. Okay, and this problem is actually NP complete deciding the solution. Okay, and people trying to use this kind of problem to build a quick system. So far, haven't. Well, there are some trial, but not really any significant ideal yet. But this is a good direction to work with. Another extreme. So that one has just one polynomial, one variable, but high degree, right? This extreme would be, well, I have lots of variables and lots of equations, but everyone has only degree 2. Okay, quadratic system, quadratic equations. Now you ask, decide, right? Or field could be F, could be just the F2, could be a small field, F2. You have any number of equations, any number of variables, and the field could be just the 0, 1, okay, F2. Decide if there is a solution. Okay, now this is kind of another extreme. This is also NP complete, so NP hard, but to find a solution. Okay, so for example, if you try to break the AES system, the encryption operation, if you try to write down all the intermediate variables, you write down the system equations, you'll see that you're going to only need to write down all the quadratic equations. They're neither change. I don't have to write down equation for that. I don't have to use variable. So all the quadratic one, you write down the new variable. So then this would be evolve about less than 2,000 variables. And then there's about 3,000 equations. You write down all the equations. If you can solve such system, okay, so with coefficient arbitrary, for example. Now, if you can solve such system, this means this you can break AES completely. Okay, basically you give a pair of plain text and private text over the two pairs. Then you can find the secret key. Well, kind of this in general, it's a question like this in computer science. So solving problem systems is like it's an NP problem. It's actually it's an NP complete. So we try to decide if there is a time argument to solve this, right? That's one of the most important problem in computer science, and also of course in science too. If you can either prove that like a solving polynomial system cannot be solved in long time, that's good for cryptography. If you can prove the integral P means there is a long time argument, then that will be disaster for cryptography. So either way, it's actually important. That's open. So I hope that gives you kind of an idea. So in general, solving polynomial system, or just try to decide if there's a solution, that's a pretty hard problem, right? Unless you can solve the NP. Well, that's kind of related to the NP complete problem. So, but in practice, we still want to say, okay, for certain polynomial system or medium size or small polynomial system size, we want to do some computation, be able to do something. Okay, so we still want to do computation. Now, so global basis actually is a essential tool if you do, especially do exact computation. If you do numerical computation, you can have different things to do. But if you want to get exact information about the solutions, the size, whatever information, right? So you have to do exact information, and global basis is the way to go. It it's a computationally extensive, but when you compute, it gives you lots of information. Okay, so here let me define this. Well, I think ideal. So there's a ubiquitous system of polynomials, and the ideal that generates all the combinations, right? So of those polynomials. Now, you fix a monomial order on the monomials. So on the polynomials, polynomial is a sum of monomials. So I'm going to introduce later on that one. So ordinarily we have to say which one is bigger, which one you have to introduce some order to a polynomial. So I'm going to give an example later on. So for given term order or monomial order, makes a subset of polynomial in the ideal, which is called the Gao basis. If every polynomial in the ideal is reduced by g, this means that there is some polynomial in g. So the leading term, the biggest term in g, actually divides the leading term of n, of f. Okay. So this basically means that the Gao basis contains all the smallest polynomial in I, in some sense, I put in it. For example, if you try to compute Gao basis for two polynomial with one variable, two polynomial, if you try to compute the general ideal, if you try to get the Gao basis, this means you try to compute GCD of those two polynomial. If you compute GCD, that polynomial, that's a Gao basis. If your polynomial is a leader system, it's a leader, right? Leader, everything's leader in all the variable, you try to compute Gao basis. That's the Gaussian elimination process. You try to get the triangular system or get the relation form. That's the Gao basis. Okay, so here's just a kind of more notation about it. So I'm going to write in terms of monomial, I'm going to write x to the alpha. So later on, I want to write all the product. I just write the x to the alpha. Alpha, and think about it's a n top of integers, non-negative integers. So it's x to the alpha means you get a monomial. So that's in 1 correspondence with n tuple. The monomial order is just the any order. You say I'm ordering in such a way. Any two of them you can compare them which one is bigger. And we say it's compatible with multiplication, means that if x to the alpha is more than x to beta, then if you multiply another monomial, the order should be preserved. So especially if you have polynomial, you have lots of terms in there. The times monomial in the polynomial, the leading term should be still leading term. The other term is still an order that we multiply. And that's sort of typo. I think there's another condition we usually use. This means that there is no infinite decreasing sequence of monomial. You could have infinite increasing sequence of monomial, but there is no infinite decreasing sequence of monomial. You can say pick a monomial, pick another one, smaller. You cannot go infinite. Okay, that's called the well ordering. I didn't mention it, but usually we want that. So the leading monomial, leading coefficient, that's the notation we use for a polynomial. Okay. Okay, so order. So maybe I don't want to define more general. Just give two examples, like a term order. The most common one, so is a lexicographic order. Means I just look at each variable. In this case, I look at the x first. If the degree x is bigger, then the term is bigger. If degree x is same, then look at degree y. In that way, it's lexical order. In this case, so because x order, then leading term is x leading coefficient 10. The next one, I look at degree first, total degree of each term. If total degree is bigger, then the term is bigger. If total degree is same, then break type by something else. For example, it's lex order. So that's we say graded lex order, right? So in this case, the highest degree is 4, that term. So that is a hidden term, coefficient -7. So that's a kind of notation I use. Okay. So we talk about Gao basis of ideal. You say, okay, with respect to, you have to say what's the monomial order you're using. Because when we change the monomial order, the Gao basis will change. So you can prove that, so I didn't mention here, but for any term order or monomial order, there is a Gao basis. And you can make this Gao basis unique if we try to get rid of redundant Gao basis, try to reduce all the terms, make it leading coefficient modic. Then for each monomial order, there is unique. reduced group basis. So you change monomial order like X change to greater order, the group basis will change dramatically. Okay. So in general, if you try to compute the group basis, the greater X order usually it's based on, well, greater the reverse X order actually it's more complicated. Reverse order usually it's when you compute group basis actually it's faster to compute. If you compute the next order, then the group basis is more complicated. It's much more expensive to compute. Because the next order actually compute the more structure, like each variable, next variable, what's the relationship, the more information. It's more expensive to compute. Okay, so when you compute group basis, actually there's a basic operation that's called a reduction. So I'm going to define this. Actually, it's pretty simple. So, but I just mentioned actually define them anyway. So, like if you have a polynomial f, the g is a subset of polynomial. I'll try to use polynomial g, try to reduce f. Okay, try to do division. Okay, so basically, f we say is reduced by g if there's polynomial g. Right? That's in the definition of group basis, right? Leading monomial g divides the leading monomial f. This means that I can take the t to be the quotient monomial, and times some coefficient, right? Then this f minus c tg, then the leading term will cancel, so the polynomial will get smaller. So I can pick a g. There could be more than one g in the set. You can pick any g, so to reduce. So that's called one reduction. S polynomial, this is the Buchberger's argument. So basically, you give a set of polynomial, you try to, well, you can reduce to each other, do this reduction, right? To each other first. Sometimes you cannot do any reduction, then still not a group basis. You have to create a new polynomial in the ideal. So in the ideal, then you try to reduce, get a new polynomial. So this is a basic way is called use S polynomial. So you have two polynomial f and g supposedly in your ideal. See, I want to create another polynomial. This polynomial basically is a combination of fg, right? I try to create a combination of fg so that the leading term will cancel. I want to create the smallest polynomial, the leading polynomial cancel. That's where this is LCM or GCD form. Okay, so take leading monomial for f, leading monomial g. I compute the LCM least the common multiple. That's where I can cancel the leading term. Smallest place I can cancel. So just I make up the coefficient. That's what it is. So you don't have to remember. It's just the one. Okay. So for example, this example I try to give the leading term, right? You can see that well, from those two monomial, leading monomial, you see where how can you cancel the leading term? Just what part x, what part y you have to make. So you can cancel the leading term. So that's for the S polynomial. Okay. So I'm going to define it how I'm going to generalize this to a general situation. Now here's the Buchberger's criterion. Okay, remember the definition was that if you give a set, I want to know if it's a group basis. Okay. Now you have to say, okay, in the ideal you have to say each polynomial you have to say is reducible by that set, right? I say it's group basis, but this ideal usually is infinite. You cannot even check the condition. See, this criteria say, okay, if I set a polynomial of the ideal, it is subset. Now it's a group basis of I. If and only if every pair of polynomial gi, tj equates that S polynomial, now you try to use g to reduce. Okay, just do reduction, just repeatedly reduce until you cannot reduce, right? Now this criteria says for every pair, this polynomial can reduce to 0. Then it's group basis. So this is a finite, well, supposed to take polynomial, you can use g to reduce, right? That's a finite process. Okay, so then you have only finite pairs. So this process you can check in finite time. Okay, so this is compared to the definition you have to check infinite minute, okay, polynomial. This is just finite minute, just reduction. So this is good, you can do it, implement it, okay, on computer. That's actually Buchberger argument is based on this. Buchberger argument is kind of simple. You just say, okay, you have originally you have a set of generator, just try to reduce each other, try to create an S polynomial, just try to do reduction. See if it's reduced to 0. If you reduce 0, that's fine. If you don't reduce to 0, you have to add it to your set. You create a new S polynomial, just do reduction again, right? and make sure all the S polynomial reduce to 0. Then you get a global basis. So your list of polynomial will increase. You will have lots of pairs. Okay. Now you make sure all the pairs reduce to 0. Then you get a global basis. So that's the Buchberger's argument. Okay. Well, that's the first argument he proposed in 1965 in his thesis. Okay. So, but after that, many years, it's not implemented because computer is not there yet. So I think in the late 70s, early 80s, or then the computer symbolic computing package, right? Developed. So now it's of course implemented in almost any computer software. Computer algebra system, like Repairable, Mathematica, any systems. Actually, so there are two issues with this. One is that the reduction actually to do reduce. You take polynomial, your system. You have to imagine when your number variable get more, like a 100 or a few hundred variable or 1,000 variable. We do this reduction. Actually, it's very expensive. But everything get big. Try to reduce to 0. That's a expensive compute. And also, there are lots of polynomial. There are lots of S polynomial. Because when the list gets longer, right? Like you have 100 polynomial in your set, or you have pair them about 100 squared divided by 2. So that better pair you have to check. Lots of pair you have to check. So it's very expensive. Another question is that people try to say, okay, how can you say, okay, detect S polynomial? Okay, this means that S polynomial will reduce to 0. The question is, how can you detect this without doing reduction? Say, okay, so take polynomial, I just look at this, but say, check some condition, right? Some simple condition. Let's say, okay, this will reduce to 0. How can I develop some criteria to do that? So that's the main issue we're going to talk about. Now, first, for the first step, how to do reduction? Okay? Faugere, the developer kind of linear algebra approach. So, okay, instead of pick one polynomial, try to reduce. He's going to say, I can pick a bunch of polynomial, try to reduce simultaneously, try to make up a matrix, and try to do reduction. So use faster linear algebra approach. So that's called F4, F4 algorithm. So I won't talk about detail on that one. People still try to implement. So my focus is on the how to detect use this polynomial part. So this will actually exist for just any person. So he called F5 algorithm. So he introduced signature and rewriting rules. So he said, okay, I can detect S polynomial without doing anything, just do some check condition. He write the algorithm. Actually, the way he presented was he write all the codes. So it's very hard to understand what he's doing. So I think, I don't know if just me or I tried several times to understand what's going on mathematically. It's very hard. So I want to actually present this argument. So I just mentioned some of the work after this one. Then, okay, actually, quite a few people try to improve this, try to simplify the presentation, right? There's Aether, Perry, there's Hashimi, ours. Recently, Perry, that the 2010 paper F5 criteria rise, that's the closest to what we're doing. I think their paper come out. Actually, we started in 2010. We wrote our paper, our first draft. I think, so I don't have actually time to describe what exactly they're talking about. Their definition is more complicated. Try to check. And there are lots of conditions in the term. So I'm going to talk about the one work with. Well, with one that also my former student, we first wrote a paper about incremental growth basis. Later on, we generalized to a general situation. Then there's a still paper come out like every year, talk about improvement or implementation issues. Okay, so like this, like every year there's two. I think there's two papers in this year. So I'm going to, okay, so I want to go into detail of any of those. So now I'm going to set up the, yes?
What does Macaulay 2 use?
I think Macaulay 2, probably they implement F4 and F5. I don't know, right now I think the new algorithm, so they try to, like our paper, they try to, I think there's some ideal, I think they developed also, I think some of the paper in 2012, 13, wrote by people like Michael Spielman and his postdoc, there's paper on that one, so they try to, I don't know if they actually put it in my code yet, but they're trying to do some experiments. How to, I think the data structure, how to do them, so actually can do faster computation. Sometimes the ideal, like the idea I talk about is just theoretical, but put into actual practice, it's not simple. It's run fast. Okay.
Are all these developments field independent? I mean, so far you haven't talked about non-zero characteristic. They're all independent of characteristic?
Yeah, any field. When we talk about that, the field can be any field, the theory is the same. But actually when you do implementation, then there's issue. Okay, so of coefficients. Like if you work with rational numbers or integers, the coefficient will grow over quickly.
I know that Grobner
So
bases
usually
are highly
field
on the order
or
and
tensor,
time
that's the issue, right?
So
If we do over real numbers, then that's a different issue.
Is it likewise highly order dependent, or does
This is vertical level, any field,
does it somehow cancel that out?
That's a good question. So yeah, good question. Okay. So yeah, I will mention that later on. Actually, even for let's see in polynomial, right? The signature order. So let's suppose if it's a polynomial T1 Tn, the defined ideal, right? Later on, define ideals. Now let me try to define also this module. That's all the coefficient, right? Coefficient vector U1 Un. Polynomial, right? Combination some order is better. Okay. So all of them together form a module. R module. So the question is that I give it system polynomial to one computable. This mean one. Okay, that's your question. We define term order, right? And also, so we said that there's no module. If they define increasing second module, you can define the term. We define the word define.
So why is there two?
So how can you conclusion? Because this one, you mean one or whether so mean one. Oh, okay. They're cooking each other. The smaller one, but they're not compatible, right? Well, we define term order. We said any two term you can. So we're gonna work it with the total order. Okay. Oh, monomial. Okay. So So it has to be total order. Word order. Order means you term the Rm, the vector type of vector. A term would be this form of monomial times the position of the EI vector, unit vector. EI is the basis. The module. Okay, then we say in our case we're not using reserve definition. That's the very common use, right? Yeah, every time you compute it, you store something in one vector. You don't have to just give it to use. So we just in our definition we just say okay, we have a pair of polynomial. You have a pair usually use Rn. So we're gonna have a term order pair on polynomial R. We just say the term order of this pair. Then this order we try to get the signature of this pair. Rm is made with the extension of U. Usually we want to compatible signature. Don't just use it. This is a very so this order Rm use it for signature weighted pair say have six. So we're gonna use location right here. B, the conditions, polynomial, and yeah, you perhaps evolve the data U, you'll see the vector, then you will come with an ideal modular term, just right there. The definition just say any pair, the signature order, you can fix order R, so that order in Rm, you can have also still have what order. But in general, just write the, now we're going to also define reduction, okay? Leading term. Reduction, just that we only have to do a total reduction. Just reduce the leading term, okay? For a pair, they come from module. We're going to define reduction. In the similar way, basically, I define image is compilation output with integer t. Okay, define the reduction with that polynomial. Look at the well, I'm going to use B1 polynomials. U1 ratio of those ratio couple and term U. So basically, the idea is among all the B2 has a combination P1, give the polynomial all the couple term. P1, T, the leading T, the signature basically the signature, the leading term of the leading signature of more than 1. Then if B2 is around 0. But if B2 is 0, you do not use that anyway, right? You just like this way. Okay, so suppose B2 is non-zero. Claim that the leading term of the multiplication process you can store divide monomial B1. You claim that every time I do a computation, the signature has a no more reduction of this property. But there's one more catch. in the condition 2. Actually, that's well, reduction. I want to make sure the TU case, look at the U part, the T